not into, but around. So I'm still struggling to do the video thing because I think it would be great. But the problem is I've read that because I'm using a headset, a Bluetooth headset, and I think the OBS when I'm using the microphone here, which is what I care the most, so you guys can actually hear proper voice. Um, then I think the whole headset is set as a headphone or something like that, and then the audio from the desktop does not come through. But maybe there's a way that I can tweak the actual desktop settings so that the audio goes through the speakers and not through my headset. You know what I mean? So that the Windows coupling or pairing with headset is just microphone, and then OBS will just do its thing. But we'll see. I have to still play with this a little bit, so I might do some test streams in the coming days. But for now, I'm still a bit confused because I'm so yeah, maybe this is a stupid picture to draw, right? But actually, I thought there was I discovered there's like a paint. I think there was like a no, was that this? No, was there was a online paint or something like that. I don't remember. JS Paint, was it that JS Paint? Yeah, that's the thing what I'm looking for. So I don't even have to open the um so does this make sense at all anyhow? Is it easy to work with? Whatever. Actually, probably doesn't make much sense, but anyway. So we've been doing Lagrangian mechanics. Let's start to paint a picture. So we start with quantum mechanics, and then kind of we realize that okay, so I realized that there's something worth taking a look at with the path integral stuff. Yeah, it's awful actually. Path integral stuff, and then uh, there's also the Schrodinger stuff. Schrodinger stuff that kind of led me to the Lagrangian mechanics. I suspect this leads me to Hamiltonian mechanics in terms of the concept because I think, based on some of the stuff that I've been reading this week, that the Schrodinger equation is nothing else than like an equivalent of potential energy plus kinetic energy, or I don't know what the usual terms for these are, but which is kind of what the Schrodinger, which is kind of what Hamiltonian says, right? Mm, But like, what is so? What is outside of that? Are these the two only things that I need to dive in, and then it's just about like grinding through the Schrodinger equation derivations and maybe seeing how kind of like these two things interconnect. Like, I am a bit lost in terms of mapping. Like, what else is there what else is there that I could or that I should be aware of? Because then this whole thing with quantum field theory that maybe I should take a look at. So quantum field theory, and it's like, where does this fit? Is this another approach to quantum mechanics? And then obviously we have the whole quantum computing stuff, which is just a specific usage of quantum mechanics. Mm, so this is more just a use case or like specifics of the use case, and but there's still a lot of things that I haven't like take a look at the quantum. So maybe what if I so quantum mechanics introduction. Uh, what does Wikipedia tell me in terms of so fundamentals, effects, experiments, formulations, equations, interpretations, advanced topics. Oh, actually, so that is a pretty good guide through. Okay, so background. So there's background, classical all quantum theory, bracket notation, Hamiltonian interference. So I think this background is something that I've more or less covered up. Then there's fundamentals, bond rule, wavelength, coherence, decoherence, complementarity, energy level, entanglement, Hamiltonian. The problem I have with this is there's a lot of different isolated topics that I'm not so they feel so scattered that I don't know. They just feel too scattered. Qubit spin superpositions, just fundamentals, then effects. Zeeman effects, Stark effect, Bohm effect, Landau quantization, and experiments. I mean, going through experiments, there will be, this is probably a great thing to do, and maybe I should go through these next, kind of like going through all the experiments, maybe one per session, or kind of like probably multiple sessions per experiment, and then kind of try to go up that kind of see where things end up connecting. The Bell test stuff. And so this is more the experimental thing. Okay, and then we've got the, what is this, for example, the Davidson electrons scattered by the surface of a crystal of nickel metal. This displayed a diffraction pattern. This confirmed the hypothesis advanced by de Broglie of wave-particle duality and was an experimental milestone in the creation of quantum mechanics. So maybe the wave-particle duality would be an interesting thing to take a look at. But I don't see anything of things like elementary particles and stuff like these. Like, oh, look at this. So elementary particles. Because I'm missing a map. Like, I'm literally missing a map of what to explore, right? I'm feeling a bit lost. So there's this whole thing with quarks and leptons and whatnot. So the elementary particles, that could be an interesting thing to take a look at. So we've got elementary particles, and we've got the experiments. As a derivatives. Okay, but then you've got the experiments. We've got formulations. So there's dynamical pictures, Schrodinger, phase space, or okay. So there's this two. So this is formulation. So what I've been playing with currently is two formulations, which I really understand them at a high level. Like, I don't, of course, know the details. I by any chance be able to make any derivation of that. And then there's this matrix things, the matrix mechanics. So that's missing. Okay, so let's do that today. Matrix mechanics. See how different that is, because this is listed as a different formulation. Okay, but I like that. Actually, that's a good map. The quantum mechanics series in the Wikipedia as a sort of a skeleton. Because there's dynamical pictures. So this is Heisenberg interaction and Schrodinger. So these are, okay, actually different pitches. And then there's phase space, which is sum over histories, which is path integral. Oh no, that's another one. Phase space. Ah, okay, cool. Yeah, let's do this. So I'll focus sort of the next I'll focus the next streams in finishing up the formulations part of things, and we won't be getting into the details of each form of the formulations, just kind of fly over the formulations. And then we'll go and do experiments. And maybe from the experiments, we'll take a look at the elementary particles. But those are different formulations. Cool. And then we've got equations. So I guess those things will pop up as part of the formulations, and there's interpretations and advanced topics. What is advanced topics? Quantum computing, quantum chaos, density matrix, quantum field theory. Okay, that is listed as an advanced topic. Quantum gravity, a bunch of things, and then scientists. Okay, categories, quantum mechanics. Okay, cool. But that's I like that. So I'm this type of person that likes to have a bird's eye view on a topic while working through these. But okay, so let's take a look at let's go back to formulations then. And I should actually just bookmark these, I think, because this takes me to the bookmarks that I've put in here. Yeah, at the end of the day, they're just part of the same thing, right? So let me just, you know what? I will basically get rid of these, get rid of this, get rid of these. What is this? Oh, that is the actual the actual category. Cool. I mean, I might keep that, but then I will just keep these. Yeah. So this is, I will call that basically table of contents or something. Cool. Okay, let's go through. So we know, so I know roughly the Hamiltonian stuff corresponds to, sorry, the Schrodinger formulation is basically a it's basically a Hamiltonian kind of concept where, you know, Hamiltonian mechanics, I guess the idea of this, just to make sure, is that uh, 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 so it's still about action, I guess. Momenta. A simple interpretation of Hamiltonian mechanics comes from its application to a one-dimensional system. So the value of the Hamiltonian in given a position momentum, I guess this is of the Hamiltonian is the total energy of the system, the sum of kinetic and potential energy, the space coordinate. Then what it says, so this is the Hamiltonian, and then function of P alone, well, it's function of Q alone. So in this example, the time derivative of the momentum equals to the Newtonian force. So the first Hamiltonian equation means that the force equals to the negative gradient of potential energy. The time derivative of q is the velocity, and so the second Hamiltonian equation means that the particle's velocity equals to the derivative of its kinetic energy. Ah, okay. So I guess that's the gist of it. Saying that if you've got the energies, you can find the velocities, and you can find the forces, which then can, yeah, because it's basically the Hamiltonian mechanics is telling you that um, that the potential energy is related to the force, and that the kinetic energy is related to the velocity, which kind of the latter makes sense. The potential energy being related to the forces, I guess it's the force. Yeah, well, it is, right? Because so if you think about the potential energy as an example coming from from gravity, yeah, well, that tells you what the force is, right? So um, if I'm really like if I'm up a hill or a building, like yeah, the sort of the floor, the how's that called? Was it like the normal force? I think it was called. So the normal force is actually what's keeping me on the on the ceiling of the building, but then the gravitational force is what wants to pull me down, and that directly relates to potential energy, right? Because the potential energy tells me that at that point, if I'm just static standing at a building, I have a certain potential energy just because of the gravity. So that seems to check, or at the intuitive level, right? I don't know what other ways to define potential energy, to be honest. Like, what are other ways to define potential energy? because it's position relative to other objects, stresses within itself its electric charge or other factors. Okay, so that may be a bit more complicated, but I guess the stressing part, it is easy to relate intuitively to forces. Gravitational center of mass, elastic potential energy. Okay, for the spring case, yeah. So if you're contracting in the spring, then you can think of the forces that the object is experiencing because of that position relative to kind of, I guess, relative to the relaxing position of that spring. With the electric potential energy of an electric charge in an electric field, uh, electric potential energy. So that results from conservative Coulomb forces and is associated with the configuration of a particular set of point charges with a definite system. An object may have an electric potential energy by virtue of two key elements: its own electric charge and its relative position to another electrically charged object. Oh, okay, cool. The whole electric stuff is something that I want to dive in at some point as well, because I have not touched that, like, ever. Electromagnetism in general, just as a note to myself. Okay, but those are potential. These are potential energies. So it's funny that you can just reduce it to position, right? It feels awkward. Like, it feels awkward that you can reduce this to position. But yeah, I guess it's position relative to other objects. That's the point, right? And that is the interaction that generates the force. So, but okay, so basically what the Hamiltonian mechanics are telling us is, you if you know the energies of a system, you can know what the velocities are, and you can know what the positions are, right? Because if you know the potential energy, you can know the position, and if you know the relative position, and if you know the kinetic energy, you can know the velocity. Sorry, the potential, you can know the forces, and so if you know the forces, you know the mass, you can know the acceleration, and all this kind of stuff. I think that checks enough for me right now. So this is the Schrodinger stuff. What is about this Heisenberg and interaction thing? So okay, but then we have the sum of histories concept, which is basically the path integral formulation, which is, here is a bit of a different picture. Here we keep track of the action. So this means not the total energy, but like how has the system changed energy wise. And that's why you have that difference where it's the potential minus the kinetic minus the potential, because that's a specific definition that allows us to define this concept of stationary action, I think was it called, right? So that this is it's a minimal function when the velocity is zero and everything is on potential energy. Yeah, exactly. And with these you can know then the stuff. But again, we're still, and this is so and this is then again, I haven't, this is all checking stuff from the classical mechanics stuff still, right? So I haven't, it's not that I have checked in the Schrodinger equation nor the path integral for quantum mechanics in depth. I guess the idea of the path integral here is that it is just a sum over all possible paths, but I don't know the details there yet of the formalism. So in classical mechanics, you just have one path, or it would just give you one path, the minimal minimal action path. And in quantum mechanics, it will give you probably a set of paths that will represent that minimal concept as well. That's the guess. That's the guess. So in quantum mechanics, dynamical pictures are the multiple equivalent ways to mathematically formulate the dynamics of a quantum system. So we've got Heisenberg, interaction, and Schrodinger. So let's take a look at them quickly. Heisenberg, interaction, Schrodinger. Schrodinger we know, right? But Heisenberg picture is a formulation largely due to Werner Heisenberg of quantum mechanics, in which the operators incorporate the dependency on time, but the state vectors are time independent. An arbitrary fixed basis rigidly underlying the theory. It tends in contrast to the Schrodinger picture, which the operators are constant instead, and the states evolve in time. Ah, interesting. I never thought about this way. So in the Heisenberg picture, the states are time independent and the operators evolve. So this means that yeah, that in a given time, your whatever operator, position operator, momentum operator would be different. And so it would affect the same state differently. While what Heisenberg is doing is like, no, the states evolve through time. Uh, okay. Weird. I guess it's a matter of taste. The two pitches only differ by a basis change with respect to time dependency, which corresponds to the difference between active and passive transformations. The Heisenberg pitch is a formulation of matrix mechanics in an arbitrary basis, in which a Hamiltonian is not necessarily diagonal, whatever that means. It further serves to define a third hybrid picture, the interaction picture. Okay, but that's actually here. The interaction picture, also as Dirac picture, is an intermediate representation between Schrodinger and Heisenberg. Whereas in the other two pictures, either the state vector or the operators carry time dependence. In the interaction picture, both carry part of the time dependence of observables. The interaction picture is useful in dealing with changes to the wave functions and observables due to interactions. Most field theoretical calculations use the interaction representation because they construct the solution to the many-body Schrodinger equation as a solution to the free particle problem plus some unknown interaction parts. So equations that include operators acting at different times, which hold in the interaction picture, don't necessarily hold in the Schrodinger or the Heisenberg pictures, because time-dependent unitary transformations relate operators in one picture to the analogous operators in the others. Unit transformation applied to Hamiltonian and state vectors. Operators and state vectors in the interaction picture are related by a change of basis to those same operators and state vectors in the Schrodinger picture. To switch to the interaction picture, we divide the Schrodinger picture into parts. H0s plus H1s. Any possible choice of parts will yield a valid interaction picture, but in order for the interaction picture to be useful in simplifying the analysis of problem, the parts will typically be chosen so that 0s is well understood and exactly solvable, while 1s contains some harder to analyze perturbation to the system. If the Hamiltonian has explicit time dependence, for example, if the quantum system interacts with an applied external electric field that varies in time, it usually be advantageous to include the explicitly time-dependent terms with H1s, leaving H0s time-independent. Okay. So time-dependent state vectors. The way most of the quantum computing stuff is being done out there right now, then it's the Heisenberg picture, right? Because everywhere and all this quantum computing stuff that's out there, like, you always assume that the states are time independent. So this is a bit of a hybrid, okay? Like we're getting a Hamiltonian and we're like treating part of it as in the time independent, part of it as time dependent. That's pretty crazy. State vector is speed time dependent. State vector is showing the picture. A state vector in the interaction picture is defined as an additional time dependent unitary transformation. The that's why changes in the state of systems energy in the system. by relating changes in the state of a system to the energy in the system, given by an operator called the Hamiltonian. Therefore, once Hamiltonian is known, the time dynamics are in principle known. All that remains is to plug in the Hamiltonian into the Schrodinger equation and involve the system state as a function of time. Even with the computer. One such technique is to apply a unitary transformation to Hamiltonian. Doing so can result in a simplified version of the Schrodinger equation, which nonetheless is the same. A unitary transformation of frame change can be expressed in terms of a time-dependent Hamiltonian and a unitary operator. Under this change, the Hamiltonian transforms as okay. The Schrodinger equation applies. Solutions untransformed transform equations are also related by U. Specifically, I guess with these. Yeah, exactly. I guess the point of this is you transform it into an easier one, and then you undo the transformation. So that's why. That's what this means, right? Yeah, exactly. Because a unitary matrix, if multiplied by itself, is the identity, or it's one. So, yeah. So then you can recover the original stuff by just multiplying it by just undoing the change. Okay. So you change the frame, do the stuff, and then change it again. So you apply the unitary to simplify the Hamiltonian, then calculate what you're going to calculate, and then revert and change back the basis. That's just the basis change idea. That's what unitary transformation means. Operators have. Okay, so that's the same thing here, is it? Time evolution. Proof. Boom. The term interaction representation was invented by Schwinger. In this new mixed representation, the state vector is no longer constant in general, but it is constant if there are no coupling between fields. The change of representation leads directly to the Tomonaga-Schwinger equation, where the Hamiltonian in the case is the QED interaction Hamiltonian, but it can also be a generic interaction, and space like surface is passing through the point X. The radial formula represents a variation over the phase. The purpose of the interaction pitch is to shunt all the time dependence due to H0 onto the operators, thus allowing them to evolve freely, and leaving only H1 to control the time evolution of the state vector. The interaction pitch is convenient when considering the effect of a small interaction term being added to the Hamiltonian of a solved system. By utilizing the interaction pitch, one can use time-dependent perturbation theory to find the effect of. Okay, so these are all just different ways different tools that will help you solve the same problem, but it's the same as a dynamical picture. So it's like you have operators, right, that act on states and transform these things. And so if you have the operators, then you can, and if these operators are time dependent, then you know how they'll change with time. And if you're going to calculate how the state is going to look like in, t+5 from now, then you just plug in the stuff and you get it. Well, the path integral is like you get a. So with the path integral, you're just having. What is the difference, right? Some of the histories is that you don't have the operators. It's a formalism. It's a formulation that doesn't have the operator concept, does it? it just has probabilities of evolution. I think that's the idea. It just has probabilities of evolving into, another state. And I think these are the transition amplitudes. Okay, but then what is, and then so what is matrix? Matrix mechanics is a formulation of mechanics created by Heisenberg. Okay, but that's the same. Okay, so that's the Heisenberg picture, isn't it? So it interprets the physical properties as matrices that evolve in time. It is equivalent to the Schrodinger wave formulation of quantum mechanics, is fragmentation. In some contrast, the wave formulation produces spectra. Okay, that is matrix mechanics. That is just this. The three fundamental papers. Okay, but that's the. So when it was introduced by Werner Heisenberg, Max Born, it was not immediately accepted. It was a source of controversy at first. Schrodinger's later introduction of wave mechanics was greatly favored. It was not a mathematical language. By Bohr, discrete energy states. The Broja had discrete energy states. Matrix mechanics, on the other hand, came from the Bohr school, which was concerned with discrete energy states and quantum jumps. Bohr's followers did not appreciate physical models that pictured electrons as waves or as anything at all. They preferred to focus on the quantities that were directly connected to experiments. In atomic physics, spectroscopy gave observational data on atomic transitions arising from the direction. Okay, yeah, but again, I think that's the same thing. And then phase space. But isn't that then the path integral phase? I think phase space. So places the position and momentum variables on equal footing in phase space. In contrast, the Schrodinger picture uses the position or momentum representations. The two key features of the phase space formulation are that the quantum state is described by a quasi-probability distribution instead of a wave function. Okay, that's different than state vector or density matrix, quasi-probability distribution. And operator multiplication is replaced by a star product. The theory was fully developed by Hilbrand, Grunewald, and independently by Joe Moya. Oh yeah, that's why the Wigner equation thing comes in, right? That's what's, I think, then used for the CVQC. The chief advantage of the phase space formulation is that it makes quantum mechanics appear as similar to Hamiltonian mechanics as possible by avoiding the operator formalism, thereby freeing the quantization of the burden of the Hilbert space. This formulation is statistical in nature and offers logical connections between quantum mechanics and classical statistical mechanics, enabling a natural comparison between the two. Yeah. Quantum mechanics in phase space is often favored in certain quantum optics applications or in the study of decoherence and a range of specialized technical problems. So that's why it's the Xanadu model, right? It's less employed in practical solutions. In the phase space distribution of a quantum state is a quasi-probability distribution. What is a quasi-probability distribution? Why isn't it that linked? The yield expectation values with respect to distribution, they all violate the additivity axiom because regions integrated under them do not represent probabilities of mutual exclusive states. To compensate some quasi-probability distributions also counterintuitively have regions of negative probability. Ah, okay. That's what it means. It means that they also have negative probabilities and stuff like this. Mm-hmm. The phase-space distribution may be treated as the fundamental primitive description of the quantum system without any reference to wave functions or density matrices. There are several different ways to represent the distribution, all interrelated. The most noteworthy is Wigner representation. Yeah. Okay, now I can. Okay, now I'm connecting some of the dots with what the Xanadu people are doing. So the state here is represented by the Wigner. Wigner. I don't know if it's Wigner, Wigner. The phase space distribution possesses properties akin to the probability density in a 2n dimensional phase space. For example, it is a real value unlike the general complex value of the wave function. We can understand the probability of lying within a position interval, for example, by integrating the Wigner's function over all momenta and over all position interval. Okay. Yeah, so you integrate a specific region and you get the probability. But it's more, yeah, so it's all really a continuous feature, right? That's being drawn in here, and actually in all in the path integral as well. So if AXP is an operator representing an observable, it may be mapped to phase space through the Wigner transform. Conversely, its operator may be recovered by the Veil transform. So there is a way you can transform an operator to something that can act on the Wigner stuff. It could take negative values, even for pure states, with the unique exception of optimally squeezed coherent states. It's not allowed precise localization within phase space regions smaller than the Planck's constant. I keep coming back to what I mean. I never remember what the Planck's constant really is or means. Cannot be arbitrary function, as it could be localized into a small region of space. Okay, there's a lot of detail in here, but a star product, a commutative binary operator in the phase space formulation that replaces standard operator multiplication is a star product represented by the symbol star. Each representation of the phase space distribution has a different characteristic star product. What is a star product, though? Left and right derivatives. Okay, that's its own thing. Jesus. Okay, it's other parts of defined as convolution. The energy eigenstate versions are known as Stargen states. Oh. Twitter. Favorite word of the day. Come on, don't be so slow. I just want to tweet. Awesome. I love how some of these names just pop up like that. They look so. Where was I? There. Targen functions, so gen functions. Okay. Yeah, look, there's so much stuff to take a look at that it's just those are different formulations. Each of these things is like it's its own big rabbit hole. Okay, so the phase space stuff is the continuous quantum mechanics thing, quantum computing stuff. Okay, cool. And this is everything, right? In terms of formalisms and like. Okay, so here's a nice summary. New quantum theory, later developments, mathematical structure. Oh, so here are the postulates. Probably I should do the postulates. Pictures of dynamics. Yeah, probably I should do that as well. Maybe to kind of close out these, and then I think that we can just go. Then I'd like to go through some of the fundamental particles, and then I'd like to go through experiment stuff. And I guess at some point we'll just pick a formalism and deep dive into this, deep dive into it. It just, what is Planck's constant? That's an energy thing, right? It's a photon's energy is equal to its frequency multiplied by the Planck's constant. Okay, so it's a constant that relates the energy with the frequency, and also the mass to frequency. Okay, and what is the reduced Planck's constant? This has to still sink in a little bit. H bar. It's just the quantum of angular momentum. Okay, so this is related. Okay, I see that. Frequency, by frequency being like it denoting sort of the region. Yeah. So it's kind of like okay, so this is something that relates, it's a constant that relates then the different energy jumps that you can do. And that's why it's like there's nothing, like we don't know what happens in between. I think that's kind of what you come up with a lot of the what time is it? How much time we have? Okay, we've got a bit more time. So where are we here? The formulations of quantum mechanics. So the postulates, I wanted to do the postulates, right? But here's like, okay, so the old quantum theory, a bit of history, I guess, direct black body spectrum, which was later used to avoid the classical ultraviolet catastrophe by making the unorthodox assumption that in the interaction could be only change discrete units called quanta. Planck's postulated a direct proportionality between the frequency of radiation and the quantum energy, and that's the Planck's constant. I had it right there. Quanta were actual particles, which were later dubbed photons. The new quantum theory, so Heisenberg's matrix mechanics was the first successful attempt at replicating the observed quantization of atomic spectra later. Okay. Later developments, path integrated phase space formulation, quantum field theory in curved space-time. Jesus Christ. C-star algebra. So there's even another formalism. Okay. But yeah, let's take a look at the postulates. The following summary of the mathematical framework of quantum mechanics can be partly traced back to Dirac, Neumann axioms. The postulates are canonically presented in 6 statements, though there are many important points to each. Yeah, but those are postulates of the Heisenberg version or the Schrodinger version. I mean, whatever, the dynamical version, right? Or what? A physical system is generally described by 3 basic ingredients: states, observables, and dynamics. A group of physical symmetries. Classical description of can be given in a fairly direct way by a phase space model. Symplectic phase space observables are real valued functions on it. Time evolution is given by a one-parameter group of okay, this is just too abstract. Quantum description normally consists of a Hilbert space states. Yeah, okay, but if we talk about Hilbert space, we're talking about some concrete formulation here, right? Okay, no, yeah, but you can math stuff. So there's this postulates, description of a state of a system. Postulate 1. The state of an isolated physical system is represented at a fixed time t by a state vector belonging to a Hilbert space called the state space. Yeah, but that is, so again, that is, yeah, that is for the dynamical picture and the path integral, but that's not for phase space, right? But you can map it, okay. State vector. Postulate 2, every measurable physical quantity A is described by a Hermitian operator, A acting on the state space. This operator is an observable, meaning that its eigenvectors form a basis for H, for the Hilbert space. It's an observable. That can be measured, okay. Position, momentum. So, but these things are defined as physical quantities. But again, that's also the dynamic picture, right? Because in the path integral, you don't have operators. And I kind of forgot why the Hermitian operator was, the Hermitian part was important. Postulate 3, the result of measuring a physical quantity A must be one of the eigenvalues of the corresponding observable A. Postulate 4, when the physical quantity A is measured on a system in a normalized state, the probability of obtaining an eigenvalue is given by amplitude squared of the probability by function. So that's okay, that's the Born rule, isn't it? Postulate 5, if the measurement of equals on the system is it gives the result an, then the state of the system immediately after the measurement is the normalized projection of this onto the eigen subspaces. Okay, so that's like the measurement problem, right? Postulate 6, the time evolution of the state vector is governed by the Schrodinger equation, where it is an observable associated with the total energy of the system called the Hamiltonian. Yeah, but that's again, that's other implications of the postulate. So these are all the postulates. Features of dynamics, this we know. Heisenberg, Dirac picture, and then we have time as an operator, spin, Pauli's principles, representations, the problem of measurement, that is the problem, list of mathematical tools. Okay, but that doesn't do a good job to the path integral stuff, right? Oh, later developments, okay. Electromagnetism resulted in quantum field theory, which was developed starting in the 1930s. Quantum field theory has driven the development of more sophisticated formulation quantum mechanics, which okay, so and quantum theory to electromagnetism. So electromagnetism is something that I also would like to check in general. But I'm getting a good sense of a map here. Maybe we could do a bit of the exercise to actually have a bit of a kind of map that we build somehow. But yeah, okay, cool. I think it's good enough for today's session. I got a bit of an overview on all the formulations already. So I think we can start next with, I'll probably, let's do the next one. Let's do the fundamental particles and maybe the wave particle duality thing that's a bit confusing as well. And then we can go through experiments. And I think with experiments, we can take a more of a deep down. So we can just really go and actually take a look at, say, the, Bell's inequality, for example, and try to look at it from different formalisms perspective as well and see what we learn there. Yeah, I think that's what it is. So the next one is going to be maybe a bit of a, or I don't know, maybe I'll do that offline. I'll see the elementary particles, and then I'll just jump to the experiments. But that's it. Formulations is nothing else than these. So you've got all these formulations, and yeah, of course, each of them is its own rabbit hole. And I mean, not even talking about advanced topics like the quantum field theory stuff and quantum gravity, which is what's, I think that's kind of the frontier of trying to connect the quantum stuff and the classical stuff, right? Yeah. Awesome. That was a good session. I like kind of the overview stuff. Have a good day.